Total internal reflection. When light travels from a denser medium to a less dense medium, for example, for glass into air, the speed of the light increases and the light refracts away from the normal. The angle of refraction is greater than the angle of incidence. The diagram shows the light refracting from glass into air. As the angle of incidence is increased, the angle of refraction also increases. Take a look. At a certain angle of incidence, the light will refract 90 degrees and travel along the boundary between the two media. This angle of incidence is called the critical angle. The critical angle varies for different materials, but it is useful to know that it is around 42 degrees for glass. The diagram shows light hitting the glass-air boundary at an angle that is equal to the critical angle. If the angle of incidence is increased further so that it's greater than the critical angle, all of the light is reflected. This is known as total internal reflection. It's called internal reflection because it occurs inside the glass. And it is called total because all the light must be reflected. The value of critical angle can be calculated by Snell's law as follows. The refractive medium is the air, and angle of incidence is 90 degrees. Sine of 90 degrees is 1, and the refractive index of air is also 1. Then we get the formula to calculate the critical angle. The conditions required for total internal reflection to occur are: the light must be traveling from a more dense medium into a less dense medium, for example, glass to air. The angle of incidence must be greater than the critical angle. Let's see how it works. The refraction index for diamond is 2.5. Calculate its critical angle and draw a figure that describes the situation of this problem. Take the values given in the question and substitute into the formula. Let's draw. The light is traveling from a more dense medium into a less dense medium. Total internal reflection in the optical fibers. Total internal reflection is a powerful tool since it can be used to confine light. One of the most common applications of total internal reflection is in fiber optics. The basic functional structure of an optical fiber consists of an outer protective cladding and an inner thin rod of high quality glass through which light getting in at one end undergoes repeated total internal reflection and emerges at the other end. Take a look at the figure. The fiber optical is clad by a material that has a lower index of refraction than the glass to ensure total internal reflection, even when fibers are in contact with one another. The figure above shows a single fiber with its cladding. Optical fibers are commonly used in telecommunications because information can be transported over long distance with minimal loss of data. Another common use can be found in medicine in endoscopes. Endoscopes use optical fibers to produce an image of inside the body. A doctor can insert a bundle of optical fibers into the body. Some carry light into the body and some carry light reflected off internal body surface back out. This allows the doctor to see an image of inside of the body clearly and help them diagnose disease. Now it is your turn.